Hi everyone, today in Integrated Math 2, we're going to go over Chapter 10, Lesson 7. Here are the objectives. Make sure you write them down in your notes. Alright, so what is a vector? When we're talking about vectors, we have a couple key terms that we want to remember. Tail is at the start of the vector, then it goes to the head, which is at the end of the vector. Notice the magnitude is the length or size of the vector. And the direction is just saying where it is going. So short vectors have a small magnitude, long vectors have a large magnitude. When we're talking about direction for vectors, there's a couple different ways that it can be shown. For example, this one here, the direction of vector A is 30 degrees relative to the horizontal. So this is a horizontal line right here. And we're saying it is 30 degrees relative to the horizontal. So it's not saying it's at the horizontal, so what it's saying is 30 degrees away from the horizontal line. In this case, it's also above the horizontal as well. Next, we have the example here. So this one is saying the direction of vector A is 60 degrees east of north. So this one, when we're trying to remember direction, so I'm going to put them up here and I'll explain it. You can always remember your directions as never eat soggy waffles. So the acronym never eat soggy waffles helps you remember the directions for north, east, south, west and where they go. So in this case, we have the direction of vector A 60 degrees east of north. Another way that we can read this is that it is from north 60 degrees east. Next we have vector addition. The sum of two or more vectors is a single vector called the resultant. When graphically adding vectors, you move one of the tails to the head of the other. So I'm going to do that for you here. Notice that the tail is moving and it's going towards the head. That's perfect right here. The result is formed by connecting the other tail and the head. So if I'm going to keep on going with this, you're going to see that we have the resultant, which is U plus V, which gives us the resultant right here. That can also be shown in the other direction if we were looking from the head and the tail from the other direction. Same thing here. Vectors on the coordinate plane. Vectors can also be represented on the coordinate plane, of course. A vector is in the standard position of its initial point at the origin. Remember, the origin is 0, 0, and always will be. When a vector is at standard position and its tail is at the origin, which is right here, the component form can be written by using the x and y coordinate of the terminal point. For this vector, we can write, notice we have our brackets here. We're going to say x, y. When a vector is not in standard position, we have to approach it a little differently. So as you can see here, neither of the vectors are in standard position. Remember, that is the origin at 0, 0. They're not there. So next thing we have is vector PQ. Okay, we want to find the change in x and the change in y. So I'm going to use the angle of brackets to do this. So if it helps, you're going to put x1, y1, x2, y2, just so that you're seeing your x's and y's, x1, y1 at the tail, and x2, y2 at the head. So when we're setting this one up, we're going to say that's -3 minus -1. So remember, this is different. I'm going to put this down here to help you out. So x2 minus x1. Notice the x's are first here. And then we're going to have -1 minus 3. So y2 minus y1. So between these two, remember that it's always going to be head minus the tail. And same thing for the y as well. So commas, head minus tail. And so the way that I wrote these, that's how it's going to work with x2 minus x1. So keep that in mind. Then you're going to change these both to pluses. So we have -3 plus 1, which is going to be -2. And we have, I'm going to change those signs, and that's going to be -4. Now at this point, we can also check this graphically. Remember, the x is going to always be the horizontal change, and the y value is always going to be the vertical change. So notice it's from -2. So remember, we're going to start at the tail, and what it's saying is a horizontal change from -2. So that means we're going to go to the left 2, 1, 2, change of x of -2, think about a number line, and then we're going to go down vertically 4, 1, 2, 3, 4, which is right here. So we know that we have ended at the head. So we know this one's correct. Now let's try the same thing for vector CD. So once again, we're going to start from the head to tail. So x1, y1, x2, y2. So we have 4 minus 0, comma, 1 minus -1. 4 minus 0 is 4. And change those signs. We have 2. So once again, we can double check our work here if we are looking at the head. So in our case, we have a horizontal change of +4. So we're going to go to the right 4, 1, 2, 3, 4, and we're going to change it. We have a change of vertical up 2, 1, 2, and we know we're correct. So I'm going to put a little check mark so I know that I've checked both of those. If we have vectors in component form, such as A, B, and CD, then we know that's going to be equal to A plus C and B plus D. And this will be the same idea for vector subtraction. We're going to subtract A minus C and B minus D. Then we have the scalar multiplication. Think about scalar as if it makes it bigger or smaller. Think about K as being distributed with a distributive property as if these were parentheses. Then we have K times A and K times B. So now we want to find each of the following for vector R, vector S, and vector T. So 2 times vector T minus vector S. So here we have 2 times our vector T, which is, oops, gotta be careful, gotta make sure you're using the brackets. So make sure it's like that, not parentheses. 1, -2, close it, minus vector S, 5, -1, oops, comma, -1. So here I just did substitution. This was vector T and this is vector S. Remember The 2 is determining the scale, so I'm going to use the distributed property for this one. Think about this one as still doing the order of operations, such as, please excuse my dear Aunt Sally, or if you like, people eat more donuts after school. So we have 2 times 1, which is 2, and then 2 times negative 2, which is negative 4, minus 5 minus 1. Alright, now let's do our subtraction. Remember, x's are going to be subtracted with each other. So we're going to do 2 minus 5, comma, negative 4 minus 1. Sorry, negative 4 minus negative 1. Don't forget all those negatives. And that's going to be negative 3. And that is going to become negative 3 as well. And there we go. Alright, next we want to find the magnitude and direction for each vector. So here we have vector C that we're going to start with. Think about these as x's and y's. So x and y. X is showing the horizontal change. And then use that triangle, horizontal change. And y is showing the vertical change. So horizontal change of 5. I'm going to make a line. Think about the horizon. So that's 5. And we're going to go from left to right. Think about this one as if you're making your x and y, your coordinate plane. This side's always positive, which means the left-hand side is negative. Going up for the vertical change is always positive, which means going down for the vertical change is always negative. So that's how I know this is still going to be positive. From here, we're going to look and see, we know we have a vertical change of positive 3. So that means it must go up. So we know we have a vertical change of 3. And with this, we're going to connect it back to the Pythagorean theorem. We have a right triangle. Let's say that's x, which is going to be our magnitude. That's what we're still trying to find. So we're going to say 3 squared plus 5 squared is equal to x squared. 9 plus 25 is equal to x squared. 9 plus 25 is going to be 34, which is equal to x squared, square root both sides. So x is equal to the square root of 34, and you want to leave it as a square root. To find the direction of the vector, we know that this one is going to be up and to the right. And what we want to know is this angle. So in this case, I'm going to say it's theta. And it's going to be above the horizontal, so between here and that line that we just made. So the way that we find theta, that angle, is by using a little bit of trig. So if we're looking here at this triangle that we have, we know we have the opposite, which is O. We're going to keep that there. And then we also know the x is the hypotenuse. We don't know what that is. Well, we don't want to use that one. We want to use the adjacent. So A. So remember, we have so, ka, toa. We have opposite and adjacent, which means we need to use tangent. So tangent of theta is equal to the opposite, which is 3, over the adjacent, which is 5. All right. But remember, we want to get theta by itself. Think about it as boxing that theta. The only way to get rid of this tangent is by taking the inverse of tangent to both sides. Now that goes away. Then we have theta is equal to 31 degrees. Alright, so remember the theta that we found is 31 degrees above the horizontal line. Or we can also show it by indicating in the picture. So we have a horizontal line, and then we can show it that it's above by 31 degrees. So now why don't you go ahead and find the magnitude and direction for vector k. If you do this correctly, you should find that the magnitude of vector k is equal to the square root of 45. And then you should also find that theta is equal to 63.4. So let's make a coordinate plane here. And you know it's going to be 63 degrees below the horizontal line. However, so let me put 63.4 degrees. And so 64.4 degrees below the horizontal line. And it's also going to be in the third quadrant. And that's it.